லைவ் ஆயிடுச்சு பாருங்க சார். இப்போ ரெஃப்ரெஷ் பண்ணுங்க. இப்போ பாருங்க. இந்த போஸ்ட் காமிக்க மாட்டேங்குது. வேற ஏதாவது எக்ஸ்ட்ரா கனெக்ஷன் போஸ்ட் காமிக்குது. ஏன் சார் காமிக்குது? நீங்க அந்த இதெல்லாம் யூடியூப்ல பார்க்கறது உங்களுக்கு தெரியுதா? நான் யூடியூப் ஸ்ட்ரீம் பண்றேன் சார், எனக்கு தெரியாது. தான் வருது இல்லைங்க சார் என்னோட சிஸ்டமே. இப்ப தெரியும். இப்பதான் தெரியுது. மைக் ஆஃப் பண்ணுங்க. ஓகே ஓகே சார். இங்க என்னோட ஸ்பீக்கர் ஆன்ல இருக்கு, அதனால கேக்குது. இப்போ ஒன்றும் பண்ணிடுறேன். So good evening to one and all joined here. So on behalf of our Department of ECE, M.Kumarasamy College of Engineering, Karur, we are welcoming you all for this international webinar on VLSI physical design. I humbly and a warm welcome to our today's chief guest, Mr. Samuel from ST Microelectronics from Singapore. He is going to deliver the VLSI physical design today's session. So it may give you some industrial exposure towards the faculty or students working in this area of VLSI design. Now I request our head of the department, Dr. C. Vivek, to address the gathering. Sir, please, sir.
Yeah, good evening, on all present here. First of all, I would like to thank our chief guest, Mr. Samuel, senior digital IC design engineer from ST Microsystems, Singapore, for accepting our invitation and also delivering international webinar on VLSI physical design. Okay, and I would like to thank all the participants who has given us a very great participation count. For example, around 200 participants they have registered. Just I inquired with the coordinator, Dr. Panvelajan. He gave me a statistics like our participants are from all over the world, from USA, Egypt, Malaysia, Germany, Turkey, Sweden, all over the world. Our participants has joined, and I would like to thank all of them. And also, many participants are from industry, like working in industry. For example, Intel, Mentor Graphics, around 35 participants are from various industries, IT sector, core sector, etc. And we are planning to conduct the webinar in 2 modes, like a Google Meet and YouTube link. I think the coordinator has shared the mail to all of them, all of the participants. And at the end of the session, there will be a feedback on the quiz session. Once you have completed the feedback and quiz, the certificate will be sent to the registered email ID. Okay. So just with this few introduction, I will hand over the session to Mr. Samuel, so that I request all the participants to interact and make use of the webinar effectively. Okay. Over to you, Mr. Samuel, sir.
Thank you, sir. Thank you for the introduction, and also thanks to your institution for inviting me today to be part of this webinar. And I hope that this session will be useful to all the participants who are attending today's seminar from all over the world. Thank you, sir. Yeah, I will be sharing my screen now. Okay, I hope you are able to see my screen.
Yeah, yes, sir. It is visible, sir.
Okay, thank you. So today's webinar is on VLSI physical design. So we will be covering all the steps of physical design. It will be from basics to some exposure on the practical side. So I will be sharing some snapshots for your review. And just a brief introduction about myself. I am Samuel Jigme Harrison. I did my bachelor's in a bachelor's in electronics and communication engineering in St. Joseph's College of Engineering, Chennai. And then I did my master's in IC design in NTU, Singapore, followed by a master's in business administration from Anglia Ruskin University, UK. So I have 10 years experience in physical design. I had 7 years experience in Avago Technologies, which is Broadcom Limited now, and then followed by ST Microelectronics, Singapore. So, and I also been part of a few technical societies, both in India and also abroad. I also published a few papers in SNUG and also an article in the Semiconductors Industry Association in Singapore. So now moving on to today's webinar, let's have a quick glance about the semiconductor industry in Singapore. The first semiconductor industry was opened in 1968, and Singapore has around 60 semiconductor companies holding around 35,000 employees. And this is a very big industry in Singapore, and it also contributes to 7% of the country's economy. So my workplace, I work in ST Microelectronics, and ST Microelectronics is Europe's largest semiconductor chip maker, and it's one of the world's largest semiconductor companies with its corporate headquarters at Geneva. So we serve around 100K customers around the globe, and with 11 manufacturing sites, and we have around 46,000 employees worldwide with 18,000 active patents. And Singapore is the Asia Pacific headquarters for ST Microelectronics in this region. So now moving on to physical design. So what is physical design? Physical design is a process which actually transforms the digital circuit representation into a physical layout. So this process is a part of the IC design cycle for digital design, where the front-end team does the circuit portion, and the back-end team does the physical layout for implementation. So physical design is the back-end portion, where the circuit representations actually are converted to geometric shapes with various metal layers. For example, in the VHDL Verilog netlist, there will be a, for example, if there is a connection from A to B using coding, in the same coding is represented as a metal layer, where the metal layer connects the two regions from A to B. So A is an input and B is the output. So the metal layer is the connection between A to B. So the functionality remains the same when you convert the circuit to a geometric layout. Only thing is the representation is different, whereas the functionality is the same. Okay, so this is the physical design location where it fits into the IC design flow. Here you have system specification, which is the data which is given to the architectural team from the customer, and the specs taken in by the architectural team, and the architecture is done, and then it comes to the functional logic and design, where the front-end team comes into play, and they design the circuit, and the circuit is given as input to the physical design team. So if you see the figures here, you can see that this is the Boolean logic, which we study as digital logic design with NOR gate, XOR gate, AND gates and all. So that representation is given to the physical design team, and the physical design team does partitioning, floor planning, placement, clock tree synthesis, signal routing, and timing closure. So these are the steps of physical design. So today we will be going through all these steps quickly, because it's a very vast syllabus to cover, but I will be just covering it as a crash course. So and we have physical verification and sign off, where we do DRC LVS checks. Then the fabrication happens, where the GDS from the physical verification, after physical verification is done, the GDS is given to the fabrication plant, which is the manufacturing companies where they manufacture the chips. So in the fabrication plant, once the fabrication is done, it is given to the packaging and testing division. So once the packaging and testing division gives their output, then it is given as a chip to the customers. So this is how the IC design flow works, and it is where physical design plays a major role in the IC design flow. So the inputs for physical design are netlist, library information, and of the cells. So it is the .lib, which has the timing informations, and also the technology file, which has the manufacturing constraints. So this technology file is given to the engineer from the manufacturing plant. So for example, if we follow the TSMC 40 nanometer process, the 40 nanometer process will have certain specific manufacturing constraints, and so they are a requirement for physical design, and the final requirement is the timing constraints to do timing analysis. So timing, power, and design constraints are to be met during physical design. So these are the three main aspects we need to take care during physical design. Okay, so what are the steps in physical design? The main steps in physical design are floor planning and power planning, placement, clock tree synthesis, routing, static timing analysis, and physical verification. So these are the main steps of physical design. And now moving into floor planning, which is the first step. So floor planning is the critical and the first step in physical design. So what are the goals of a good floor plan? So the floor plan in physical design is same as the floor plan we first draw for when you build a house. So it is the same, like where do you place your hall, where do you place your kitchen, where do you place your bedroom, where do you place your balcony. So all this is like pre-planned. The same thing happens when you do floor planning in physical design, like where do you place your macros, where do you place your pads, where do you place your IPs. So all this has to be taken care of. So what are the goals of a good floor plan? Goals of a good floor plan are you have minimized chip area, because the customers and the clients and our management, they usually look for designs with a small chip area. So they always want our die size and the chip area to be smaller. So the goals of a good floor plan are minimize total chip area, routability of the design should be routable. If there is congestion and when you enter the routing step, you are not able to route the design, then it is all your work has been wasted. So your good floor plan should result in routability of the design, and then minimal congestion, and also low power consumption. So all these are the goals of a good floor plan. So in case if you have more congestion and then you put in different efforts to fix the congestion, that may result in high power consumption. Because nowadays we are working on very low technology nodes, and the main concern for the customers is low power consumption. So we need to have the consumption of power as low as possible. Okay, so what are the steps in floor planning? The steps in floor planning include size of the chip, determination of size of the chip, I/O pin placement, macro placement, creating standard cell rows, and adding routing and placement blockages. So we will see each step in detail. Okay, so this is for the size of the chip. So floor planning is controlled by two parameters. One is the aspect ratio and one is the core utilization. So aspect ratio is the width to height ratio of the chip. So width can be related to horizontal routing resources, and height can be related to vertical routing resources. So the chip usually has vertical and routing tracks for metal layers to be placed during routing. So those tracks are known as the resources available. So aspect ratio is number of horizontal routing resources by the number of vertical routing resources. Okay, so in floor planning, if your aspect ratio is 1, then it means the block shape is a square, because your vertical and horizontal resources are the same. But if your aspect ratio is greater than 1, then your block shape will be rectangular with more routing resources in the vertical direction and less routing resources in the horizontal direction. So your height is greater than the width. And if your AR, the aspect ratio is less than 1, then your block shape will be rectangular with more routing resources in the horizontal direction. So your width is greater than the height. So all these are basic theory for you to understand before you do your floor plan die size estimation. And the second thing is the core utilization. So the area occupied by the standard cells and macros, and that is the percentage of area used for cell placement. So okay, so core utilization is you have an area for standard cell placement, and you also have your area for macro placement. So this both combines the total area available in the chip. So the core utilization is equal to the standard cell area plus the macro area divided by the total core area. So this gives you the core utilization. For example, if the core utilization is like 0.7, then it means that 70% of the area is used for cell placement, and only 30% is used for routing. So if your core utilization is like more, for example, if it is 0.8, then you have only 20% for routing, which is a very tight resource. So you need to make sure that your core utilization is as less as possible. Only then you will have more freedom when you do your routing. So this is the balance we have between the utilization and the routing resources. Okay, so this is the second step, the core rows placement. So the standard cells will be placed in the chip. So the height of the standard cell determines the spacing between the core rows. Core rows is nothing but the areas where the standard cell is being placed in continuous rows. So the width of the core row is determined from the height of the standard cell. So these standard cells are available from your library team, and each project will have different types of standard cells. They will have 13 track, 9 track. So it depends on the tracks. The standard cells height will be different. So when you place the standard cells, you need to make sure that the core rows are the alternate core rows are flipped. This is why, because you consider one core row and you place a standard cell A. So the core row at the top will have VDD, and the core row at the bottom will have ground. So when you place the standard cell on the core row, the top portion is VDD and the bottom is ground. And subsequently, in the adjacent core row, if you place it, place it without flipping, the top portion will be still VDD and bottom will be ground. So this VDD will short with the ground from the previous core row. So that is the main reason we flip the alternate rows, so that the VDD overlaps and ground overlaps. So that is the main reason, because if your VDD and ground shorts in the cell, then you are not able to tape out the chip. So this is the main reason we use alternate rows. So the standard cells will be placed alternately, so that the VDD is overlapped and ground is overlapped, and there is no short. Okay, so how do we determine spacing between macros? A minimum spacing must exist between macros for pin sites. For example, the channel spacing between two macros is calculated by number of pins into pitch divided by the available layers by the total layers. So the pitch should correspond to the topmost layer. For example, if you have two macros facing opposite to each other, one macro has the highest metal layer as metal 4, other macro has highest metal layer of metal 3. We need to take the pitch from the metal 4 layer to calculate the channel spacing. So as far as possible, we need to avoid open spaces in the design. Unwanted spaces should be avoided, and unwanted spaces like very small spaces left out should be covered by placement blockages. That I will deal later. Now regarding macro placement, we need to make sure that the pin of the macros should always face the logic area. Because if the pin of the macro, if it faces the opposite direction, then there is a long route happening. So we need to make sure that the pin of the macro always faces the logic area, and you always use a data flow diagram as reference. So this data flow diagram is given to you by the customer. So each block or chip will have a data flow diagram, so that you will able to know like which macros communicates with which macro, and how is the placement need to be done, and you can have it as a reference. Because there will be a case where there will be a group of macros which communicate within each other, so you need to place those macros close to each other, because if you place those macros far away from one another, then it will cause you unnecessary routing resources and also congestion. So you need to understand your floor plan well, and we need to make sure that the routing channel between the macro is big enough, so that it accommodates signal routes and also sometimes power strips. So the signal routes, meaning the pins which come from the macros, should have routing resources to be routed properly during routing. So we need to give that spacing. macros can be also be abutted if they belong to a same group, and they can be abutted together to reduce the space consumed. So when you abut the macros together, you need to make sure that the pin sides are opposite outward direction. Okay, now looking into blockages, there are two kinds of blockages. One is the placement blockage and one is the routing blockage. So these blockages have you have to place it in the floor plan step. So the placement blockages, this also prevents placement of standard cells, buffers and inverters. So placement blockages must be used in thin spaces between macros. Because if you leave a thin space between the macro which is uncovered, then later during placement step, the tool may place a standard cell in that location. So which will cause unnecessary long routes and congestion when it tries to route that particular cell. So to avoid it, wherever there is very minimal spaces, we need to put placement blockages in order to make sure that during placement step, the standard cells are placed only in the center core area. And the second one is the routing blockage. This also prevents routing of a metal layer in the blocked region. For example, if you have a signal routing in metal 4 and you have few macros which has metal 4 routing, so when the signal route occurs on that memory with metal 4, it will create a short. So in order to avoid it, when you put a routing blockage, metal 4 routing blockage over the top of the memory, and when you in that case you can route your signal routes can be placed over the memory so that it doesn't create a short. So that is why we put routing blockages. So routing blockages has to be put in for power pad through the VDD and ground power stripes. So these power stripes are usually use the wide and highest routing layer. For example, if you have a chip with 6 metal layers, metal 6 will be your power stripe, which is your VDD and ground. The standard cell rails. So this is a very important aspect in power planning. We need to make sure that all the standard cell rails where the standard cells are placed are properly connected to VDD and ground. So these rails are used to supply power for the standard cells. So the cells are connected to the rails through the follow pins. Follow pins is usually in either metal 1, it's mostly in metal 1. So metal 1 and metal 2 will be the follow pin. And if you have a chip with 6 metal layers, metal 1, metal 2 will be a follow pin, which is also VDD and ground connecting to the power stripe. 3, 4, 5 is for signal routes, and metal 6 is for your power stripe. So maybe metal 5 will be for your it will be helpful for your clock routes. So signal routes will be in metal 3 and metal 4. This is how we structure the chip before we start work. So the row orientation of alternate standard cells is flipped so that the standard cells are connected to both VDD and ground. This is what I explained you, that we need to flip the standard cell rows so that the standard cells are placed alternatively is flipped. Okay, so IO pads placement. This IO pad placement is very important. We need to ensure that placement of sufficient number of VDD and ground pads is required on either side of the chip for uniform distribution, and power dissipation and IR drop should be taken into consideration while deciding the number of VDD and ground pads. So we need to also ensure that there is proper connectivity of VDD and ground pads to the entire area of the design. Now, if you see here, this is a small representation of standard cell core area VDD ground, where you have VDD and ground at the 4 corners, and here you have the horizontal one, which is the trunk, and here you have the VDD and ground pads, and the rings are here, so that in between you have the standard cells placed, and there are the core rows. So if you see here, everything is interconnected. So from bottom to top, all the connectivity should be proper. If in case there is a missing connection in this area, when you do in this area to VDD or ground, when you do your power analysis, there will be a hotspot here. So the power analysis tool will help you identify that you have a missing connection in this area, that the VDD and ground is not properly connected. So then you have to again come back to your floor plan to check it. So what happens is, in industries, once floor planning is done, we usually do a rough power analysis to see the issues, so that we clear off it in the very early stage, instead of waiting till the chip is routed and then we find out this issue. So this power analysis is done in intermediate steps. So it's done in the first step and at the last step to make sure that everything is perfect. Okay, so this is an example of you have like you have a region here, and this region is surrounded by VDD and ground. So this is the block ring. So you have the block ring which is covered by VDD and ground. So this is how a design will look like after you do power planning. So you have commands to do power planning. You can also implement it as Unix script, or you have also the option in this Innovus GUI to do the power planning for block ring placement, follow pin routing, everything. You have an option. So here you can see that the follow pin rails are placed now. You can see that this one, the top portion will be VDD, and this one is ground. So okay, here if you see, the top portion is the ground. You can see that the connection is made to the ground, and the bottom one, the connection goes to the VDD. So if the connection goes to the VDD, there is no connection in the ground. So here you can see that the top one is the ground, which is connected to ground, and the bottom one is the VDD. And here the VDD and ground is also connected. So this is how the this is the end result of power planning. All your follow pins are connected, and also your power strips are done, and also your block rings are done. Okay, the third step is the placement step. Okay, so what are the objectives of a good placement? So objectives of good placement is timing and power, minimum cell density and pin density, routable design, good control over congestion, and minimum timing DRCs. Timing DRCs is max capacitance and max transition. So always a good placement will lead you to will make life easy for you as you move on to the next steps. But attain a good placement, you also need to have a good floor plan. So only if you have a good floor plan, you are able to get a good placement. So every step is interlinked, and we need to make sure that floor planning is done properly. Okay, so what are the steps of placement? We have 3 steps. One is global placement, which is the first step. It takes 50% of the runtime. So here the tool actually finds an approximate location to place the cells. So the placed cells are overlapping with each other, and they are just like a rough placement of the cells. The tool puts in all the cells into the core area. So, but this one is not visible to us because the tool does it. So this is the theory behind the placement. So this placement of standard cells is timing and congestion driven, because now in Innovus we have features which is to set like the timing, the placement engine is timing and congestion driven to make sure that the placement of cells, during placement of cells, timing and congestion are taken into account, and tool places it accordingly. So the placed cells are overlapping with each other, and they do not align the power rails. So this placement technique is quite fast, very fast, and it is accurate for the initial timing and congestion analysis. So this is how it looks like. You have standard cell rows. This is the core row, and you have standard cell placed here, and you have the macros. So here you can see that all the cells are put in, and it is overlapping with each other, and they are not properly placed in the standard cell rows. This is the first step, which is the global placement. Second step is the legalization. So this is where the proper placement takes place. Tool moves all the cells to the legal locations. Legal location is the standard cells should be placed in 4 rows. So that is a legal location, and then and also the cells are aligned to the routing tracks. And since everything is legalized and the cells are placed properly, it is automatically connected to the power and ground. The third step is the detailed placement, and this is actually minor modification happens where the small location of small modules are moved and few standard cells are adjusted. But the main placement step happens in legalization. So this is how the placement step happens when you run the command for placement. Okay, we have a feature called placement bounds. Placement bounds are we module groups of if there are certain standard cells which communicate within each other, and if the tool places it very far from one another, it will create unnecessary routes and congestion. So what we do is this constraint actually controls the placement of the group of standard cells. So if a particular group of standard cells, they communicate with a particular macro, we club them together at one location and closer to the module, so that lots of unwanted routes are avoided. So this is the principle of the placement bounds. And we also add spare cells. They are also a part of the standard cell library. They are known as spare cells, and they are dummy cells which are actually inserted in the netlist. So the reason we add these dummy cells, the spare cells, are later once the chip is taped out and it goes to the industry, and the customer comes back to you saying that we have a version to be added, so we need a version 1.1 change. So we only need this particular feature to be added in the chip. So what we do is the chip again comes back to the netlist team and also the physical design team. The netlist, the front-end team, they add the codings required for the feature, and the back-end team will add that particular cell in this removing the spare cell. So when we have spare cells spread in the design, it is easy for the engineer to remove the spare cell and add in the required standard cell for the function, so that there is no other impact in the chip. Suppose if you don't have spare cells in the design, what happens is when the customer comes back to you for a change, you are not able to add it because you don't have spare cells in the design. So this actually happens in many companies, and it is a very big loss for the industry. So we need to be careful that always spare cells are added as part of the placement process, so that later when there is a request, it replaces the standard spare cells with the standard cell. So this is a difference between a good placement and a bad placement. So for a good placement, you can see that the cells are placed properly and the fly lines, the connections are neat. Whereas for a bad placement, you can see that there are the connections are everywhere and it's a mess. So when it's a mess, following clock tree synthesis is a problem. Routing is not possible, and your chip implementation step is delayed. Okay, so what is the difference between a good placement and a bad placement? So good placement helps you to decrease the area of the chip and also the length of the wires, because it's obvious when you place the modules close to each other, your net length reduces. So when your length of the net reduces, automatically your power consumption is reduced. So when you have more nets in the design, your power consumption is more. Since power consumption is a big concern for many companies now, and the products are all dependent on power, we need to make sure that the length of the wires are as short as possible in the design. And the bad placement results in increase in area and length of the wire. So the other difference is good placement will result you in easier routability, and you will have more routing resources, and your routes are very neat, so it helps you in timing closure. Whereas bad placement will help routability to make it life difficult. The good placement also has shorter wires, so there is less power consumption, whereas bad placement has long wires with power consumption. And then good placement has less hotspots, and there are less congestion issues, so you have maximum performance. Whereas bad placement, when you have more hotspots, when you try to fix these hotspots, you will add in more buffers or something to fix the timing, which will result in your degradation of performance. Okay, the important feature of placement is congestion. why does congestion occur? Like congestion occurs if the number of available routing resources is less than the required routing resources. So in this case, congestion occurs, and during each step, you have when you open the database, the GUI will have a feature. You can check the congestion map. So the congestion map you can check for each layer, and you can identify like which layer is creating a huge congestion and where is the location, so that you can debug into that location and see how you can improve it. Either you can modify the floor plan, or you can group the cells together. So all this comes by trial and error. So once till you become familiar with the working of this process, you have to do lots of iterations in floor planning and also placement. Okay, so what are the basic reasons for congestion? High standard cell density, creating hotspots, and no proper placement blockages, less routing resources, placement of macros in the center of the chip instead of the boundary, and tool does buffering during I/O placement, resulting in lots of cells. These are the reasons of congestion. Okay, the strategies to fix congestion. You need to identify areas with low utilization, because some areas may be congested, but some areas the cells will not be placed in those areas. So you need to make sure to find ways to spread out the cells, and you need to modify the floor plan accordingly. And can also spread out the top level ports during floor planning, so that it will help you to ease congestion. And also you can also increase the spacing between macros. If there is like too many pins in one group of macros, and it creates loss of congestion, then you can place the macros apart. And also you can add proper blockages. You need to make sure that you add proper blockages. And also you do the block resizing to reduce the overall congestion. So block resizing to reduce overall congestion is the last step, because usually it is not advisable. Only the worst scenario, we do resize the chip or the block. So we need to first analyze and see why we cannot fix congestion with the present floor plan. And we need to ensure that the macro pins always face towards the logic region. Okay, so this is a result of placement, where you can see that the cells are placed in between now. Previously, we only had the power routes. Now you see the cells placed, and the cells, this is the inner layout of the cell, where we have metal 3, metal 2 connections inside the cells, and this is the internal routes being drawn. So each standard cell. So usually there will be, in some companies, physical design team engineers will build the standard cells, individual standard cells. It will also go through the same process, and they will build the standard cells separately, and then the standard cells will be integrated into the chip. So for each nanometer technology, the companies will have the standard cells ready. It will be stable for each technology, so that when you get a project, if it's a 40 nanometer project, all the standard cells of the 40 nanometer library will be installed in your database. And when you source your environment and you import your floor plan, all the 40 nanometer cells will be in your design. So all these are already, they will run through all the physical verification checks and make sure that the internal to the standard cell is clear. Okay, so this is actually a result of placement. Like during placement, actually a trial route occurs. So once the cells are placed, you can have a picture like how your design will look like, how your routes will look like later. So this is an example of a trial route. Okay, so the fourth step is clock tree synthesis. This is a very major step, and this step helps you to fix timing. I'm sure that this module will be quite useful for you. So as we move on to this step, we need to make sure that our floor plan is very good and our placement is also very good. So usually once after placement is done, you will check for setup time, because till clock tree synthesis, the clocks are not propagated. So you cannot, the tool will not report hold time violations. So it will only report setup time, which is on the data path. So you need to understand the setup violations, and if it's a very drastic violation like failing by 10 nanosecond, you need to see why it is failing by 10 nanosecond. Something around 100 to 200 second placement step is okay during the first run of placement route. And during placement step, you need to also make sure that your density is between 50 to 60 or 60 to 65%. Anything above 70% or 80%, you need to check and you need to make sure that your density is less. If your density is more during placement step, then when you come to synthesis, clock tree synthesis, and when you go to the route step, it is even worse. So there are some cases where the tool is not able to route because of this density issue. So you need to make sure why your density is bad, and an acceptable density is usually 50 to 65%, or the max is 68, 70%. Then you need to check for horizontal and vertical congestion. In placement step, horizontal and vertical congestion should always be less than 1%. If it is more than 1%, like 2%, 3%, you need to understand why it is so bad. There are some chips, very small chips with few metal layers, like they only have 5 metal layers in the chip. Even though your density and your congestion is 1 to 2% or 2 to 3%, you can even still route and close the design. So depends on the complexity of the chip, you need to analyze your violations accordingly. Okay, so the fourth step is clock tree synthesis. Clock tree synthesis is a very critical step in physical design. So you need to understand it properly, where you have a clock in the design, and this clock is communicating with all the flip-flops. So all the registers are connected here. So when you do a timing analysis, the distance between these two is very small, whereas the distance between this and the last one is very long. So when you compare these two, this is a very short route and this is a long route. So in this case, it is very hard for you to balance the clocks and close timing. So in order to avoid it, you do clock tree synthesis, where this is broken into clock like tree-like structures, and intermediate buffers are added. So when intermediate buffers are added, it quickens the process, and it quickens the transmitting time from the clock to the register, and so it balances the whole scenario, and it is easy for you to close timing. So this is the main requirement of clock tree synthesis in the chip. There are some chips, even they can close timing without clock tree synthesis. So, but for major, very critical chips, very large chips, clock tree. Okay, so what are the objectives of clock tree synthesis? You get a minimum skew, you get a minimum insertion delay, your maximum maximum transition, and your maximum capacitance. So you get a minimum skew, and your timing DRVs are clean in clock tree synthesis. Okay, what are the effects of clock tree synthesis in the design? One portion of clock tree synthesis is it helps you to close timing and helps you to balance the clock. But the worst part is it adds clock buffers and clock inverters. Clock buffers and clock inverters are not like a normal buffers and inverters. They consume more power. So if your floor plan is not good and if your placement is bad, when you do clock tree synthesis, the tool will automatically add lots of clock buffers and clock inverters in the tool to facilitate this clock tree synthesis. So what happens is it will add more clock buffers, clock inverters, resulting in more power consumption. So in order to avoid it, we need to have a very good floor plan and a good placement. And also, when you add more clock buffers and more clock inverters, it increases the congestion in the design. So now, how is CTS achieved? Addition of clock buffers and inverters is the major reason for CTS, and also CTS is achieved by minimizing the skew and to meet the max tran and max cap violations, and also to balance the clock. And non-default rules is applied to clock nets, and also shield is applied to clock nets. So all this will contribute to for you to achieve the CTS. Okay, the next one is clock buffers and clock inverters. Clock buffers are used for clock tree building, and clock buffers are used for clock tree balancing. So this is the different use of clock buffers and inverters. And clock buffers have equal rise and fall time. So that is why we use clock buffers and clock inverters for CTS. We don't use the normal buffers for CTS because normal buffers, they don't have equal rise and fall time. And clock buffers are increased in size than the normal buffers. So all this you need to take into account. So once you do your clock tree synthesis, you need to open your report and check how many clock buffers and inverters are added. The lesser, the better. If it's lesser, then it means that your floor plan, your placement is good. That's why the tool didn't add many buffers and inverters. Okay, so this is a launch clock and a capture clock. A small definition of a pictorial representation. So this is a launch clock in this register, and you have a combination logic here, and you have the register here. So with a flip flop, and then this is the launch clock, and this is the capture clock. The difference gives you the skew. So if the distance between the launch clock and the capture clock is more, then the skew is more. So in order to minimize it, we have to find methods. Okay, what is min delay and max delay? These are some basic definitions which will help you in interviews. Launch clock, and there is a launch clock and a capture clock, and this is a clock cycle. So the min delay is the rise of the active edge, and the max delay is the one delay in one clock cycle. So the delay in one clock cycle gives you the max delay. And what is a skew? Skew is difference in clock arrival time between two registers. So if you have two registers far apart, and the difference in the clock arrival time gives you the skew. And our main aim in clock tree synthesis is to minimize the skew. And clock insertion delay is the delay from clock source till registers. So here you have an pictorial representation. I will show it later. Like the delay from clock source till register, which is the source latency and the latency. Okay, so this is how clock tree synthesis is done. This image is before clock tree synthesis, where you have one clock and it communicates with all the registers. And this here, the clock is balanced now, where you put intermediate clock buffers to balance the scenario. There are two ways of clock tree synthesis being done. One is a clock mesh. Previously, many companies were using clock mesh, but the problem with clock mesh is the tool will put a full mesh over the chip, and it actually contributes to more power consumption and more area taken in, because even if there is no requirement for a clock tree buffer to be added at a particular location, you will still have a clock mesh there. So now companies are using clock tree synthesis, clock tree structure, where the buffers are added only at the required regions. So only at the required regions the buffers are added, which is helpful for power consumption and also helps you to reduce congestion. Okay, so how do you achieve a proper clock tree? We pre-route the clock nets. So we have three steps in routing. First one is the power route, which is done in power planning step, and the second one is the clock routes, which is done in CTS, and the third one is the signal routes, which is done in the route step. So the pre-route of clock net is done in clock tree synthesis. So this is the first priority of routes, and you use higher metal layers for clock tree synthesis, and which is wide width, and also you do shielding of clock nets. So this is a representation of how a clock net is shielded. So you have a clock net, and the clock net will be surrounded by VDD and ground nets. So this is it acts as a shield for the clock net. So it is a must that all clock nets should be shielded, and you need to use higher metal layers. Non-default routing rules should also be applied to clock nets. These rules actually consist of double wide triple wide metal with double spacing. So all these rules are given to us from the manufacturing side. So they follow the design rules given to us for 40 nanometer. 40 nanometer will have standard NDR rules. So we need to make sure that they are all aligned, and these rules are only used to route the clock nets and not the signal. Okay, so this is how clock tree synthesis is done. Here you have a GUI. Once your clock tree synthesis is done, you can open up the database, and in Universe there is a CC-opt debugger window. So when you open this window, you can see how your clocks are balanced in the design. This is actually same representation of the design, but only the clocks are shown in. And you can see that here you have the clock trees, the tree-like structures, and the clock skew for each. If you click on this, buffer, you can see the skew, the min delay, max delay, all the name of the buffers being added. And here you can see good balanced structure of the clock tree. So if you have a balanced structure of clock tree, then it is easy for you to close timing. So at the end of clock tree synthesis, you will report both setup and hold time, because in clock tree synthesis the clocks are propagated. So you will report both setup and hold time, and you need to make sure your congestion is under control, and you need to analyze your hold time first to see whether you can fix your hold time and what are the major issues in hold time. Maybe you can tweak, you may have to tweak the latency of certain clocks in the clock tree spec. So you need to analyze your clock tree synthesis. So everything comes by practice. As a fresher, when you go into the industry, if you have your basics good, then you can understand the structure well. But all this it comes by experience, and how do you balance the clocks, and how do you analyze the clock tree synthesis reports. Everything comes by experience. Okay, the fifth step is routing. Routing, now looking into the goals of routing. In routing, we minimize the total wire length, we minimize the bath delay, we minimize the congestion hotspots, we minimize the number of metal layer changes. So this is very important. We need to make sure that the number of metal layer changes is reduced. If you have more number of metal layers being changed, you need to, for every change of metal layer, you need to add a VIA. A VIA is an interconnect between the first layer and the second layer. So when you keep adding vias and you keep changing layers, it will contribute to more power consumption. And we need to complete routing without increasing the total area of the design. So this one we need to make sure that the routing is completed without increasing the area. And also good timing closure and meeting timing DRVs. So this is a basic requirement of routing. So routing order in the physical design process is like how I mentioned. First is powering, second is clock routing, and now is the signal route. The signal routes are the rest of the nets in the design, because the entire routing process is completed for power nets, for clock nets, and left out is only the signal nets. So the left out resources can be used for signal nets. Okay, so routing grids are defined in the entire layout. We have horizontal routing tracks and vertical routing grids. And also routing direction is defined for each metal layer. Vertical routing direction, metal 2 will have a horizontal direction. Metal 3 will have a vertical routing direction. Metal 4 is horizontal. So this is how it works horizontally and vertically. So the metal layers, the directions cannot be same in the consecutive metal layers. It should be like alternate layers will be horizontal and vertical. Here you have a pictorial representation where you have a vertical routing track and you have a horizontal routing track. So vertical routing track is metal 1, horizontal routing track is metal 2, vertical routing track is metal 3, horizontal is metal 4. So this is the alternate positions of the routing. Okay, now you can see here that you have a standard cell here, and you have a metal 2 wire being routed, and you have this is a VIA interconnect. VIA interconnect is nothing but it connects the previous metal layer with the next metal layer. So this one is VIA 1. So then you have a metal 1 layer metal 1 net, and then here you have again a VR and metal 2 to a standard cell. Here the standard cell will have the standard cell pin, and this net connects to the pin, and here this net again connects to the standard cell with metal 2. So this is how a physical layout will look like. Okay, what are the stages of routing? As discussed earlier, placement has 3 stages. One is global placement, legalization, and detailed placement. Same is for routing. We have global routing, track assignment, and detailed routing. So this is global route, where the routes are not finalized. It's just a trace of routes being done. The tool does a trace of route, which is global routing. But all these are internal to the tool. We won't see it with our eyes. We will only see the end result. So this is the theory behind routing. So this is global routing, and objectives of global routing is to minimize the overflow of congestion, to do a routing which is less congested, and also reduce total wire length and reduce the runtime. There are 2 types of routing. One is time-driven routing and crosstalk driven routing. In placement, we have 2 types, which is time-driven and congestion-driven placement. So time-driven routing is wire delays are calculated, and the tool will make sure that it will try to put in the routes as short as possible. In time-driven routing. In crosstalk-driven routing, it avoids section of long paths that run parallel to each other. So if you have 2 nets running parallel to each other, it will create crosstalk violations. So in order to avoid it, the tool will make sure that there are no long continuously running in the tracks. So the second step in routing is tracking assignment. Track assignment is a stage where the routing tracks are assigned for each global routes. So assigning horizontal and vertical tracks depending on metal layers and rerouting all the overlap wires. Same happened in placement, where legalization fixed all the overlapping cells. So here track assignment reroutes all the overlapping wires. And detailed routing here is the final route is output of your route step after all the overlaps are fixed. Okay, so this is a layout of how a route looks like. So once your routing is completed, this actually is your congestion map. So if you see that the areas in blue here are all less congested, and as it goes in the center you have yellow. Yellow is like moderately congested, and here you have red and orange. This is like highly congested. So you need, once you see this, you need to go into your database and see why is this area congested. Is there any timing nets, like there are long nets here, or is there any like loops of nets in this location, or is there any standard cell creating congestion? You need to understand and see why. Or if you have more congestion in this area, subsequently when you do DRC analysis, you will have more shorts and spacing violations in this area. So if you fix it during route step, then it is easy for you when you do the physical verification process. Okay, so as I mentioned, routing is also crosstalk driven. So this is the signal integrity check done during route to see if to make sure that 2 nets are not close to each other for a long time. So the affected net is the victim, and the switching net is the aggressor. So if the 2 nets are continuously parallel to each other for a long period of time, then if you crosstalk violations. So how do you fix this crosstalk violation? You limit the length of the parallel nets, and so that you can create a jog in between, so that the continuity is broken, and you shield these special nets. And also you can upsize the driver or buffer. So upsizing driver or buffer is the last option, but whenever you create a break and you create a jog of the net, then it automatically fixes the violation. Okay, so this is how routing is done. Here you can see that all the nets are being routed here. Now all the nets in the standard cells are routed. So this is the end result of routing. But after routing, if you see here, you have some left out spaces. So this left out spaces is not advisable. in physical design. So you need to do something to fill up these left-out spaces. So after routing, there is an option to do filler cell placement. These filler cells actually they are added after routing optimization. So they are actually used for power rail connectivity to fill up the gaps. So if you see here, there is a vacant space, and if the cell is missing in this location, the power rail connectivity is lost between the standard cells. Because here you have standard cells, here you have standard cells, here is an open location. So what you do is, if you put in these filler cells, the filler cells they have no function. They are only used to fill the gaps in the where the standard cells cannot be placed, so that the power rail connectivity is maintained. So the filler cells they contain only N-well, P-well, and power rails. That's all. So now the filler cells are put in, and now your design is complete. Okay, the next one is static timing analysis. Static timing analysis is a very big module to be discussed. So here we will just look into the basics of static timing analysis and a few examples of how setup and hold time occurs. Okay, so what is STA? Static time analysis is one of the techniques used to verify the timing of the digital design to make sure that we meet the timing constraints. So STA can only check the timing and not the functionality of the design. So what is setup time and what is hold time? I think it will be good if I can explain this with a pictorial representation. Here you have a clock path and here you have a data path. So what is setup time? Setup time is the time required for the data path here to be stable before the active clock age. So if the data path is stable before the active clock age, it is setup time, and if it is active, it is stable after the clock's active age, it is hold time. So this is the basic definition behind setup and hold time. So before and after it can toggle, but during this period it should be stable. That is the setup and hold time window. Okay, so what is the required time? It is the time required for data to arrive at a certain point. This is the basic understanding of requirement. And arrival time is the time at which the data arrives at a certain point. So the slack is the difference between the required time and the arrival time. So you have positive slack. If you have positive slack, then your design is met and you don't have timing violation. When you have negative slack, you need to fix it. So negative slack means the design is not meeting time. If your design doesn't meet timing, then the management will not allow for a takeout unless there is some proper waiver for hold time or setup time. Or setup time sometimes can be waived by few picoseconds, 1 or 2 picoseconds or something. So setup slack is the required time minus arrival time, and the hold slack is arrival time minus required time. Okay, so what is positive slack? Positive slack is required time is greater than the arrival time, and negative slack is arrival time is greater than the required time. If you see this image here, you will have a clear understanding of positive slack. So in positive slack, your required time is greater than the arrival time, whereas in negative slack, your arrival time is greater than the required time. So that is the launch clock and the capture clock. That is what they mean as required time, arrival time is your launch clock, and capture clock is how it works. Okay, so clock latency in the design is your slow source latency and unit. Source latency is nothing but the clock source to the boundary of the chip. So this is the clock source, and the network latency is the full circuit here, where you have your inverters are there, your resistors, flip-flops are there. So all this delay contributes to your network latency. So combining both gives you the clock latency. Clock skew is the difference in arrival time of the capture of two adjacent resistors. For example, here you have a launch clock here and you have a capture clock here. So if ahead of capture clock, it is positive skew, and if your launch clock is delayed from your capture clock, it is negative. So this is the difference between positive skew and negative skew. And now, what is the timing path? A timing path actually consists of 3 elements. One is start point, combination logic, and the end point. Start point is the point in the timing path where you start your analysis from, and it goes through lots of combination logics in the design, and then it reaches an end point. So start of the timing path is where the data is launched by the clock edge, and it is actually start point will consist of input port, input delay, and all. Combination logic, it contains and or XOR elements. All the functionality of the design comes in the combination logic area, and endpoint is all the buffers, inverters, all adding into the combination logic. Endpoint is where your timing path ends. Okay, so timing paths are of 4 types. In this pictorial representation, I can explain it clearly. Here you have a data, and here is a flip-flop register. So this data to the register is the input port to register, and this register to this register, and here you have logics. So the register to register. This is this register to register is the main critical path in setup and hold violation. Because this to this distance, this timing path, it depends on the combination logic in between and the location of the combination logic in between. So if the cells are placed far apart, then the path is a very long path. Analysis, and this is registered to the out, so reg to out. And we have one more timing path, which is the in to out, input port to output port. So it just depends on the placement of your input port and output port in the design. Okay, so how do you fix setup violations? Setup violations can be fixed by upsizing the cell. You insert buffers and you reduce clock uncertainty and you increase delay in the clock. Upsizing the cell is a very easy method to fix setup violation, or you can insert buffers. Reducing clock uncertainty is a last resort for you to work out. So this is the steps to fix setup violations, and the steps to fix hold violations. You can add delay, you can detour the route. So detouring routes will help you to fix hold violation, and you can downsize the cells too. The last option, use data path cells with high threshold voltage, is also possible, but when you add delay, you downsize the cell or you detour the route, usually it helps you to fix hold violations, unless there is some critical path where hold and setup fail on the same path. So that is a very challenging process for you to fix setup and hold both on the same path. Because when you say fix setup, your hold will violate. When you fix hold, your setup will violate. So we need to analyze the path carefully and see what is the best we can. Okay, so this is actually how does a prime time timing report looks like. I'm sure that the participants from the industry are well aware of this one, but this one I just put in for the engineering graduates and also the freshers, so that it will give you an idea of how a timing report looks like, and when you go for an interview or a new job, it will be helpful. So here we have start point and end point. So the start point and end point is belongs to one clock group, and the path clock group is I clock. So the path type is max. If path type is max, it is known as setup. It is known as a setup timing report. Whereas if path type is min, it is known as a hold one. So we need to make sure that the start point and end point belong to the same clock group. If it belongs to different clock groups, for example, start point belongs to I clock and end point belongs to S clock, then it is not of the same clock group, and paths are asynchronous. So this we need to check. So now you see the arrival time here. Data arrival time is 739 picosecond. Sorry, 739. 739. Our required time is 10059. So the slack is 9320. So your required time minus arrival time, it gives you 9320, which is a very good value. So your slack is met. So this is an example of a positive slack. Here you see this is a setup check where your phase shift is required time is 10 nanosecond, slack time is 9 nanosecond, and your arrival time is 0.827. So here also arrival time you see here is obtained through all the flops present in a DFF flop, inverter, all these will contribute to your arrival time. So this is how your required time, your slack, your arrival time is calculated. So now you have a positive slack of 9.1 nanosecond because your required time is 10, but the arrival time is 0.827. Now if you see here, this is an example for a failing timing report where your type of check is hold violation and your begin point is IN1 and your endpoint is seg1/U3/D. So there are different clock groups, and also the other end arrival time is 0.682. Required time is 20.648 and your slack time is minus 20 nanosecond, so which is a negative slack. So your arrival time is 0.117 and your required time is 20.648 and you have a negative slack here. So all these are time reports available for once you complete your time analysis. Once you complete your actually in each step of your physical design, in placement, clock step, post clock, route, post route, you will have timing reports being generated by Innovus. So you can intermittently check all these timing reports to clear out the violations, and later sign off for the design is usually done using prime time, which is from Synopsys. So the timing engines are different from prime time and cadence. So the STA engineer will give feedback to the design engineer on where to fix all the violations in the timing failing parts. Okay, the final step is physical verification. We have few more slides on physical verification, and by that we will come to an end for today's presentation. So for physical verification, these are the basic theories and rules behind physical verification, which is DRC, layout versus schematic, electrical rule check, XR, and LEC. So, but now in the industries we have more lots of new checks being done. But these are the basic checks being done in the industries. Design rules check is the DRC process where the physical design database is checked against the design rules. Design rules is provided for you from the manufacturer, TSMC or some company. For each technology, these design rules are provided by the manufacturer, and DRC should be cleaned before the chip is passed out to the foundry. So what are the types of DRCs? We have minimum width of metal layer, shorts, minimum spacing of metal layer, minimum width of spacing for vias, minimum area enclosures, different net spacing. All these are the basic types of DRCs. So I have few pictures here for you to understand it better. Okay, this is a shot where you have a purple metal layer, which I guess is metal 3, and the vertical, the horizontal one is metal 2, blue in blue. So here you have, say for example, this is clock net A, this is net A, and this is net B. So here you see a short. So how do you fix this short? You can extend this metal layer here, so that here you have a straight route and doesn't short with this net. Okay, the spacing violations are here. Here if you see that this region has a spacing violation with this metal 2 net. So how can you fix it? You can extend this metal 3 over here, and then here you can do the change of layer from metal 3 to metal 2. So here if you change the layer from metal 3 to metal 2, this will help you to fix the violation, fix the short spacing violation, because here you have less space, so that is the problem. Okay, min area violation is where you when you have vias and we have metal layers like this, metal 2 extended like this, there is certain requirement for the metal 2 layer to be extended further away. So that is why they put in this layer. So when you extend the metal layer furthermore, your mean area violation will be fixed. So the tool, wherever there is a VR put in, the tool will expect there should be a certain minimum metal extension. Okay, what are the basic DRC checks? The basic DRC checks for physical design is width of the metal layer and spacing between two metal layers and area enclosure of vias. So when you put the via in the center, you need to make sure that there is spacing, proper spacing enclosure. Okay, second one is layout versus schematic check. So this one is actually what happens during this step is the tool will do analysis and checks the net list from the two outputs. So it will take the schematic netlist from the input of physical design, which is the initial netlist which we used from the front end team. So this netlist and the GDS, the physical layout is like the place and route steps you have completed so far. This will actually generate your netlist. So these two netlists are compared. So this is the source netlist being used as an input to physical design, and this is the extracted netlist from the output of physical design. So these two netlists are compared to make sure that the layout and the schematic is the same. Schematic is this one, and layout is the same physical representation of this schematic. So you need to make sure that these two are the same. So if it is the same, then it is clearing your LVS, and LVS fixing LVS is a bit complicated. So there are some projects where we have a big nightmare fixing LVS. So what are the types of LVS errors? Opens, shorts are very common LVS errors, and because from the LVS report, it is very hard for you to find out, understand the short. So it is better for you to open your route database, post route database, and you always fix your shorts in Innovus. So it is as far as you clear up your physical violations in Innovus, then you do these checks, because these checks are not being done by Innovus. These checks are being done by either Caliber or some other tool. Caliber is from Graphics. So here we have an unbound pin. So this violation is like if the pin don't have a geometry, like in physical layout we don't have this geometry, but the connections are present in the netlist. So this unbound pin is reported. Like the connections will be present in the netlist, but the pins in the data physical layout will not have the pin shape. So only when there is a pin shape, the tool will do the route. If there is no pin shape, it will not route the net. So this will report as unbound pins. Okay, this is an example for an open connection, where you see here that these two has to be connected, and there is a open here at the buff net. And here is the short. These two purple metal layers belong to the different nets, but they are shorting here. So what you do is you just pull this metal layer to this region, and this will fix the short. All these are like basic examples of how a short and open looks like. But in your real workplace, the shorts and opens will be very complicated, and sometimes you will have less. Everything will be quite congested, and to fix a short, you will have to detour the route and you have to reroute the net. So that is how it works. Electrical route check. This one is electrical route check is a mandatory check to check the robustness of the design, and both schematic and layout are checked against electrical routes. So it also helps to check floating gates, floating interconnects, shorter drain and source of a transistor. So all this. So the basic mainly the companies check for is floating gates, and if there is any short between the drain and source. The XOR check is run when the original and modified databases are compared. So this is how it's like when you have a GDS ready, you have completed all your physical design steps, and the GDS is ready, and you give it to the customer. So the customer comes back to you to saying that you have to modify few layers, like say metal 2, metal 3, metal 4. All these 3 layers has to be modified, and they give you certain modifications to be done. Like you need to disconnect this metal layer from this net, and you have to connect it to a different net, and you have to add a few nets. But your check should be, your modification should be only on metal 2, metal 3, metal 4. So this one is after tape out. So what happens if you accidentally touch metal 5? So if you touch metal 5, it is a huge loss for the customer, because for each layer they have to create the mask. So that is actually millions of dollars. So what happens is you have the original database with you, and you modify the database. You modify the database according to the customer's request. You modify metal 2, metal 3, metal 4, and you do a XOR check. So this XOR check will give you out a report. This XOR check is only between the two GDS, and you give out a report saying there is change in metal 2, metal 3, metal 4. It won't say that what is the change. It will just give out a report saying metal 2, metal 3, metal 4 has been modified. So if only metal 2, metal 3, metal 4 has been modified, this is well and good. But if there is modification in metal 5, then you have to go back in your modified database and check what has happened, and you need to rectify it. So this is a check which will help you to find out if any other module layers are modified. And the logic equivalence check is the LEC. Here actually in physical design, the design passes through lots of steps. Like place and route is done, ECOs is done, optimization is done, lots of optimizations are happening. So during this optimization process, we don't need the function of the chip to change. So for that to check, we have this step where the initial netlist is taken, where the initial netlist is from the front-end team. This initial netlist is taken, and the final netlist from place and route from physical design is taken, and logic equivalence check is done. This is known as conformal. It's also known as conformal. So this check will make sure that even though the netlist has gone through physical design, has gone through lots of steps, the function of the chip has not changed. So the source was the same, and the output was also the same. The function of the chip has not changed. So this is why we do the logic equivalence check. So all these are like basics of physical verification, but in industries we will have a lot more checks, like antenna checks, and also the crosstalk violations. All these are like additional checks, and also we have perk checks, and also many other checks are being implemented now. But these are the basics of physical verification. So this is how it works. So you have an RTL, module is modified. So then you check whether it is logically equivalent, and the RTL modification and synthesis is done. Now after synthesis, to check whether it is synthesized correctly without modifying the function. And then from the synthesis netlist, we do place and route. Physical design happens here, and we have the place and route netlist, which is the output of the physical design. So during this physical design process, we do CTS, we add repeaters, we do place and route, we optimize the design. Lots of optimization happens. So everything is happening, but we need to make sure that the function of the design is still the same. There is no change in function. If there is a change in function, then it's a very big problem, because our customer request is different, then our output is different. So if this LEC check fails, then we cannot tape out the chip. So this is a very critical check being done. So with this, we come to an end of today's webinar. It was a very it was like a crash course, but I hope I have covered the basics of all the steps, and it was useful for everyone who attended it to brush up the basics, and also to understand the different issues we face in the industry. So if you have any other clarifications, you can write to me, or also you can connect with me in LinkedIn. So, thank you. And once again, I thank the management for giving me this opportunity, and I hope this session was helpful to each one of you.
So thank you, sir. So thank you for your wonderful session.
Thank you, sir.
Was very nice, and a lot of fruitful information we got. Right. Now I am requesting participants, if you have any queries, you can directly post to our guest. Questions now. If you have any queries. No? Fine. Sir, once again I thank Mr. Samuel, design engineer, ST Microelectronics Singapore has immediately accepted our invitation and joined for this international webinar on VLSI physical design and share your views. So since our students are getting some theoretical knowledge in the classroom, but your presentation gave him some industrial exposure. So how these kind of things happening in your industry. So that will be very good, more beneficial for the students. So on behalf of our Department of ECE, M.Kumarasamy College of Engineering, Karur, I thank you very much, sir, for your wonderful session. Thank you, sir. Thanks a lot. And on behalf of our HOD also insisted the same, but he is having some other meeting. So he asked, convey his regards to you on behalf of him. So thank you so much, sir. Thank you so much. Thank you so much.
Sir, thanks for the opportunity also. Thank you, sir.
Fine, sir. Fine, sir. Thank you, sir.
Thank you.
And participants, the feedback quiz link has been shared, right, in the text box, the chat box. So you please fill this feedback link. If you have any clarification or help, you just contact the number. And this link will be valid till 8 PM today. So you please complete this feedback, and your e-certificate will reach your registered mail. And finally, I have to thank all the participants, those who have joined in Google Meet as well as in YouTube link, for spending your valuable time, for listening his fruitful session. I hope this session will help you somewhat. So we will meet soon in the future also. Thank you all the participants, and thank you Mr. Samuel for session. We will have an association in the future too. Thank you, sir. Thank you so much. Fine,
Thank you,
sir.
sir.
Thank you.
Bye.
Bye, sir.